In the previous module, we discussed the structure of the atom, specifically how electrons, in order to achieve a full outer shell, can either be handed off, collected, or indeed shared, forming ionic or covalent bonds, respectively. Acidity relates specifically to the concentration of H+. H+, of course, being an atom of hydrogen which has lost a single electron. Of course, given your understanding of the structure of the hydrogen atom, this results in H+, otherwise being equivalent to a single proton. This proton is often considered as H3O+ in water, where the H+ is transferred onto H2O. An acid is a substance which can lose one or more equivalents of H+, and a base is a substance which can pick up H+. If we look at the equation just below on the board, as you can see, we've shown a general formula for an acid, which is written as AH, or sometimes as HA. In the case of B, which is our example base here, you can see that H+ is transferred from the acid onto the base. This results in the formation of BH+, shown in blue, and the conjugate base A-, shown in red. Bear in mind that, as with all things chemical, matter is conserved, which means what is on one side of the equation must also be replicated on the other side of the equation, and that includes the balance of charges. When an acid, AH or HA, reacts with a base, H+ is transferred. And when we're considering acidity, we look at the concentration of H+, the concentration of protons in a given solution. Water, which is a universal solvent for the vast majority of ionic reactions, as we'll see in the next lecture, is considered amphoteric. The term amphoteric basically means that a substance or system or compound can act either as a proton donor or as a proton acceptor. And water is an example of an amphoteric compound. There are, of course, others which are ionic, and we may touch upon them a little later on. But for now, what you should be content with is that HA, our model acid here, can protonate H2O to give rise to H3O+, okay? Otherwise known as the hydronium ion. B, a base, can also react with H2O to give rise to the hydroxide ion, shown in red on the second part of that equation. It can also react with itself and ionize itself, forming a mixture of hydroxide and, of course, H3O+. As most acid-base reactions, as I've said, take place in water, it is common not to include the water directly in the equation. So you'll often see acid-base equilibria, acid-base equations, written as the following, where HA is shown to separate or lyse into A- and H+. And a base, shown here as a neutral species, although sometimes they are ionic and negatively charged, reacts with H+ to give BH+. So these are the two types of compounds or types of equations I'd like to introduce to you in this lecture. What do we mean by equilibrium? Equilibrium is very important when discussing any reaction, but it's particularly relevant when we're talking about acidity. So, for example, if we look at some very strong bases, it's naturally assumed that virtually every single part of that compound is converted into H+ and its conjugate base. And that is shown here in the first equation. HA, which is our model acid, disproportionates into H+ and A-. But there can also be, in the case of weaker acids, a backward reaction, where H+ and A- come back together again to form our non-dissociated HA, which is our model acid. This equilibrium is shortened, as you can see at the bottom part of the board, where HA is shown to be in equilibrium with the H+ and conjugate base A-. So, in other words, what this means is we have a reaction going forward, where we have HA separating out into H+ and its conjugate base, and we have the reaction going backwards. And this is how it is often described. And when you see these single-headed arrows going in opposite direction, you know that what you're dealing with is a dynamic equilibrium. And that's important for a whole number of different reasons. After a certain time, the speed of the forward reaction will be the same as the backward reaction, and the concentrations of the reactions and the products will remain stable, or will remain steady state. That is to say, the concentration of either the products nor the reactants will then change, unless there is influence externally by varying, for example, temperature or pressure. The system is said to be therefore at equilibrium. So, this is a model reaction which would be applicable to not just acid-base, but also to a whole number of different reactions, where we start off with two starting reactants, A plus B, that are converted into C and D. So again, irrespective of what reaction you're talking about, reactants, products. The equilibrium is always given as the combined concentration of products over the combined concentration of reactants. The brackets there around the C denote the concentration of C. Likewise, the same for D, A, and B. So as you can see, an equilibrium constant is given by the concentration of one product multiplied by the concentration of the other product divided by the concentration of a reactant multiplied by the concentration of another reactant. Bear in mind, this equilibrium is a thermodynamic property, and there's a fundamental difference between that and kinetics, which is something we may touch upon in future modules. But crucially speaking, these are thermodynamic, and therefore this does not relate to the kinetics or the rate of formation, but rather whether or not it is energetically more favourable or less favourable for the reaction to occur. So here, as I've said, where X is the concentration of X, K is the equilibrium constant. If K is large, as you might expect, what this means is that the reaction will give mostly products, with only small amounts of reactants remaining, because effectively K is just a ratiometric measure of how much product we get in comparison to how much reactant remains. However, if K is small, only a small amount of product is formed, and the majority of the compound will remain as the reactant. In the case of the dissociation of water, which I've shown you before, where you can get H plus and OH minus, which for the sake of argument is represented as A minus in this particular equation, shown on the board, you can see that the equilibrium constant for this is the lysis of one concentration of acid, HA, into H plus and A minus. And so, in this particular case, we can denote the equilibrium constant for this dissociation as, in this case, the acidity constant, or Ka. Sometimes you'll come across other equilibrium constants which are specific, for example, for complexation, and they are often given as Kd, which is the equilibrium associated with dissociation. But Ka is specifically how much of H plus is created from a given concentration of Ha. The acid dissociation constant, which you will find in any textbooks which deal with this subject, is always given as K subscript A. If therefore A is large, it stands to reason that HA, our acid, will be almost completely dissociated, giving a large concentration of H plus. This is common in strong acids. Strong acids being H2SO4 or sulfuric acid, HCl or hydrochloric acid, or HNO3 or nitric acid. These are all good examples of strong acids, where because Ka is so large, it is uniformly accepted that the concentration in each of these cases directly correlates to the imparted concentration of H plus in a given solution. Acids which only dissociate to a small extent are called weak acids, and these possess a small acidity constant, or Ka. A good example of these are the carboxylic acids. We'll be discussing carboxylic acids and the influences on their structure in a bit more detail in Module 3. But for the moment, hopefully you can appreciate that where we have an organic acid, such as the carboxylic acid shown in this particular case, the actual preference is largely for the formation of the acid and not dissociation to the conjugate base, or carboxylate, and the H+, which is obviously the measure of acidity. A good example of this is ethanoic acid. So this is given as CHCO2H, where the Ka is 1.8 times 10 to the minus 5, considerably smaller. The structural effects on acidity is something that relates to the concepts of electronegativity and also inductive effects, which we covered back in Module 1. Since the process of dissociation generates ions, there is an advantage to stabilising the product ion to give a stronger acid, if indeed that is what you require. If you recall, we talked about the idea of introducing more electronegative atoms onto less electronegative atoms. An example being, of course, chlorine being attached via a sigma covalent bond to a carbon. We indicated that in this particular case, because of the greater electronegativity of chlorine, the bond would be polarised. Indeed, the probability of finding electrons would be further moved towards the chlorine atom, because it is more electronegative, pulling electrons away. The actual physical impact on this, as we can see in the case of this trichloroethanoic acid, is to actually render this compound more acidic. And this is because in each of the cases where we have a carbon-chlorine bond, the chlorine is pulling electron density away from that carbon, which in turn is trying to pull electron density away from the carboxylate group, shown as the negative charge on the product side of the equation. By stabilizing this negative charge, you're essentially making this particular forward reaction more likely to occur, resulting, of course, in a greater concentration of H+, or protons. So therefore, the inductive effect of chlorine in this particular case, although many halogens would have the same effect, fluorine in particular, helps to stabilize the negative charge on trichloroethanoic acid as shown above. And if we were to, again, use dichloro or monochloro ethanoic acid, as you can see at the bottom, we move from the strongest acid, which has the greatest amount of electronegative substituent, all the way down to the weakest acid, which lacks any electronegative substituent. So, note the difference between strength and concentration. Strength relates directly to Ka, the acidity constant, for a given dissociation. Concentration, on the other hand, relates purely to the amount per litre of a given ion. Strength refers to Ka, and concentration refers to the amount of acid actually in solution. So therefore, it's possible to have a concentrated solution of a weak acid or a dilute solution of a very strong acid. Concentration is measured in moles per litre or moles per decimeter cubed. And what you often find is it's referred as mole dm to the minus 3 and sometimes just as capital M, molar. Acid strength can be measured using Ka, as we've already indicated. The larger the Ka, the greater the degree of dissociation of the acid into the conjugate base, and of course the important H+. But these are not generally convenient ways of measuring it, because you have to use, again, standard form in this case. 1.8 times 10 to the minus 5 is a little bit more difficult to work with, especially if you're looking at it from a biological perspective, and a lot of the calculations may appear to be confusing, may result in some errors as a consequence. So as a consequence of this, pKa is used, with the small letter p denoting negative log. That's all P means in this context. So we take whatever the value of Ka is, and then we carry out the negative log to the base 10 of that value. By carrying out the negative log to the base 10, we get a value which is a bit more easy to deal with. Usually a value running from 1 through to 14, or at the very least a decimal value which is easy to deal with. If we look at this equation, what we mean is, by taking pKa, we are taking the negative log to the base 10 of the concentrations of H+ multiplied by our conjugate base, A-, divided by the non-dissociated concentration of our acid, HA. So if, for example, we were to look at ethanoic acid, we see that the pKa of this calculation results in a value of 4.77. The stronger acid, trichloroethanoic acid, results in a pKa of 0.70. And as we actually go down in terms of pKa value, we're increasing the degree of dissociation and increasing the concentration of H+ that is actually formed. When an acid or a base is added to water, the concentration of H+ will change. And this is the origins of the term pH. pH, like pKa, in this case, just means that we're taking the negative log to the base 10 of the concentration of H+ in solution. Hence the term pH, derived from the German expression potens hydrogen. Pure water has a pH of 7. And there's a relatively easy rule of thumb to bear in mind with this. When the concentration, for example, is approximately 1 × 10 to the minus 7 in terms of moles per litre, then you can actually just remove that minus 7 and remove the negative value. So in other words, if I have 1 × 10 to the minus 7 moles of H+ in a litre of water, I will have a pH of 7. So sometimes there's a general rule of thumb which doesn't require you to use a calculator. Therefore, if we had a concentration of 1 × 10 to the minus 2, we can just take that power, remove the negative value, and we end up with a pH of 2, which you should appreciate is an acidic pH. Remember, pure water has a pH of 7, and it also dissociates to a small extent. Acidic solutions will always give a greater concentration of H+ than exists in water and have a pH of less than 7. Basic solutions will have a smaller concentration of H+, free in solution, and have a pH greater than 7, always. Typically, physiological conditions result in a pH of around 7.4, although obviously that varies depending on whether or not you're talking, for example, about urine samples, saliva samples, or indeed plasma, blood samples. Let's get on to bases. So we've talked about acids, we've talked about the dissociation of acids into conjugate base and H+. Now let's talk about bases. So there are a number of different bases. These can be charged bases, such as hydroxide, or these can be uncharged bases, for example, like ammonia and amine derivatives. What happens in the case of a base, as we said before, is that it can attract H+, or a proton, resulting in the formation, as you can see from this particular equation on the board, of BH+ and OH-. Okay? BH+ being the conjugate acid in this particular case, as opposed to the conjugate base as we saw in the case of acidity. As with the acids, the strength of the base can be shown by the equilibrium constant, in this case, Kb. And this results in pKb also being able to be determined. However, and this is something to bear in mind, more commonly you will find that in the interests of clarity, a base strength is actually measured by pKa. Now, this is not, contrary to understanding, the loss of a hydrogen or a proton from the base. This is the loss of the H+ from the formed conjugate acid. So this equation here, as you can see on the board, this shows that BH+, which is our conjugate acid, dissociating to give us our free base and our H+, correlates actually to a dissociation or acidity constant pKa. The equation for this is shown on the board. Weak bases therefore have very low pKa values, and strong bases have very high pKa values. And when we consider any acid or base, we need to know, or should be aware, that pKa plus pKb is equal to 14. Strong bases include things like sodium hydroxides. Indeed, mostly every hydroxide is regarded as a strong base. And as we said before, in the case of hydrochloric acid, sulfuric acid, and nitric acids, they're considered to be almost completely dissociated in water. And so therefore, in the case of our NaOH, we see that sodium ion and hydroxide ion are formed in solution. Now, of course, what you'll be talking about, you may wonder, is, well, we were talking about pH being potens hydrogen. We're talking about H+. So where does OH- come into this? We're not measuring OH- when we're looking at pH, we're measuring H+. And this is because OH minus will bind with any residual or large amount of residual H plus in water and convert it back into water because of the equilibrium of H plus and OH minus in water and the preference for it to exist as non-ionized water. This decreases the amount of H plus in solution and therefore increases the pH, making it more basic. Amines are also examples here of weak bases. Remember, we had weak acids. You can also get weak bases. And here we see the pKa. Remember, that is the equilibrium constant associated with the dissociation of the conjugate acid being 9.25. Methylamine is 10.66 pKa. And the equilibrium in this particular case for ammonia, and this is how you would form ammonium hydroxide solution, is where we have our base, NH3, which is a neutral base, abstracting a proton from H2O to give us NH4+, a complex cation, otherwise known as the ammonium ion, and OH-, hydroxide ion. So let's have a look at some example calculations. What is the pH of human blood when H+ is equal to 4.0 times 10 to the minus 8 moles per decimeter cubed? Okay, this is a molar concentration. So let's see how we would work this out. First and foremost, we have our concentration of H+. So relatively all of it's been done for us. All we need to now do is carry out the minus log to the base 10 operation on that concentration. And this gives us, as I said before, a result of 7.40. That is the pH. Bear in mind that because we're talking about a logarithmic operation, there are no units. Okay? So if you hear the words pH, it is merely a number. Let's have a look at the second question. Let's see what would happen if we used a strong acid, hydrochloric acid, and we dissolved it up to make a solution of 0.02 molar, which is, as I said before, 0.02 moles per decimeter cubed. The concentration is given for us here as 0.020. So again, it's relatively easy to work out because, as I said before, strong acids are completely dissociated and therefore the concentration that you add correlates directly, in this case, to 1 equivalent of H+ for every 1 equivalent of HCl added. So where we have a concentration of 0.020, we can do the negative log to the base 10 of that and give us a value of 1.70, generating a solution which of course is a lot more acidic than 7.4, which we had in the earlier question. Now, let's look at it in a bit more depth. What happens if we have a concentration of hydrochloric acid and the pH is found to be 3.55? How would we work out the concentration of HCl that we actually added? What we then do is we take the inverse log of minus 3.55, reversing the equation and giving us a value of 2.82 times 10 to the minus 4 molar. The other unit for molar is moles per decimeter cubed, or moles per litre. The inverse log is represented as the antilog, or sometimes as 10 to the x on your calculator. Right, okay, let's have a look at another example calculation. The pH of a 0.015 molar aqueous solution of HNO2, nitrous acid, was measured as 2.63. What is the value of Ka and what is the value of pKa? Okay, so this requires a little bit more application because we have the concentration of HNO2. That is to say, the non-dissociated, at the point of entry, HNO2 nitrous acid. We have the pH, which, as you should recall, correlates to the concentration of H+ in solution. And now we're being asked to work out what is the ratio between the two. What is the ratio between the starting material, the non-dissociated HNO2, and the H+ and NO2-. So let's start off by drawing this equilibrium. Remember, we said before, an arrow going in one direction and in the other suggests that we have a system which is in equilibrium. That is to say, at steady state, the concentrations of both sides are remain the same as they would do a little later on. So HNO2 goes to H plus and NO2 minus. And so what we need to do is put what we know about those particular components into an equation. So the concentrations are H plus is equal to NO2 minus. We make that assumption because we are assuming in this case that the majority of H plus comes from NO2, from the dissociation of HNO2, and also because with every dissociation of one equivalent of HNO2, we must therefore get one equivalent of H plus and one equivalent of NO2 minus. By doing this, we are able to say that the concentration of HNO2 actually within our equilibrium is given by our starting concentration of HNO2 minus the concentration of H plus. If the pH that we are measuring of this solution results in a concentration, as we can see here, of 0.00234 molar, it enables us to substitute those values into the equation to determine Ka. If we look at that a bit more closely, what we are saying here is that the concentration of H plus equals the concentration of NO2 minus. Therefore, the product of this, NO2 minus and H plus, must be equal to 0.00234 multiplied by itself. The remaining amount of non-dissociated HNO2 is given by our starting concentration minus the amount which has been converted, which we know from the concentration of H plus. Therefore, the Ka for this particular equation, for this relatively weak acid, is given as 4.33 times 10 to the minus 4. And the pKa as a consequence of the negative log to the base 10 is given therefore as 3.36. Now, I want to draw your attention to the fact that at the moment we've only been dealing with monoprotic acid. So that's hydrochloric acid, nitric acid, and also, as you saw, nitrous acid. But some acids, and this is very important when you're looking at, for example, phosphate buffered saline solutions within medical practice and so forth, is that you can lose more than one proton. And therefore, it's possible to have more than one Ka value for each successive deprotonation reaction.
Successive removals become more difficult as the molecule, therefore, bears a greater charge, and pKa values, as a consequence, get bigger.
So let's have a look at phosphoric acid here. Phosphoric acid, that's H3PO4, when reacting with water, yields oxonium, H3O+, and a phosphate anion, hydrogen phosphate anion. And the Ka in this first case is actually reasonably high, 7.1 times 10 to the minus 3. However, successive deprotonations until we eventually result in the loss of all hydrogens and only the phosphate remains is a bit more difficult to achieve, giving us a Ka value, or Ka3, for the third deprotonation of 4.3 times 10 to the minus 13. Polyprotic acids are often used in buffer solutions, and certainly when you're looking at trying to mimic a plasma or the natural pH and natural salt concentrations for a given biological system, you would often use phosphates in your buffer.